In classwork 6, we look at the sum, the difference, the product, and the quotient of functions. What you have to be careful of is your domain. Because you have multiple functions, your domain has to be taken into account for all of them put together. If one has a domain restriction, they all are subjected to that domain restriction. We kind of do this like your compositions. F plus g at x is f at x plus g at x. We take your function of x and we add it to your function of g. For the difference, we subtract them. Only remember, when you subtract more than one term, you have to put parentheses. Your product, we multiply them. And your quotient, we divide. We no longer have to rationalize a denominator if it has a radical, but you do have to worry about your radical in terms of your domain. So here's a good example to start with. We have two functions, f and g. We're going to add these functions together. So we're going to take your f and we're going to add the g. And all we're going to do right now is combine like terms. So we've got an x squared plus 4x, and you can see the ones will cancel out. This is now the rule for f plus g at x. It's kind of like your f of g rule. We're now going to evaluate that rule when x is 2. So we're getting 2 squared plus 4 times 2, which gives us 4 plus 8, gives us 12. The tougher one is the divide. First thing we have to do is find a domain here. And we've got two restrictions because we see two square roots. So let's take a look at the first one. X would be greater than or equal to 0. So on my number line, here's my 0, I would have a domain of this. I have a second restriction. 4 minus x squared is greater than or equal to 0. We factor our quadratic. We set them equal to 0. And so it's x is negative 2 and x is 2. We place this on your number line. And this is where we test your quadratic. We test the sections. But looking at this quadratic, the negative is making this turn down. So we can see that your positives fall right in the middle. There's a little bit of an overlap here. And your overlap shows right here. They both have to meet the right conditions. So they both have to share the same condition. So your domain here is from 0 to 2. When you set up your divide, f of x over g of x, you put your f of x on top, your g of x in the denominator, and you don't have to reduce, we don't have to rationalize your denominators, but we do have one little problem, and that one little problem is this denominator. Not only can it not be negative, but now it cannot be 0. So now we've got to lighten these circles up. So the domain has changed. The domain for this will be 0 to 2 with a soft bracket. If we did the divide in the opposite way, g of x over f of x, we put g of x on top and f of x on the bottom. Our domain now is restricted a little further because of our denominator. X in this case can not only be negative, but it cannot be 0. So now instead, you are lightening up the 0 and keeping the 2 dark. So we're going to go from 0 to 2 for the domain. We don't have to rationalize that, but we do have to worry about its domain. Another example of finding the domain of a composite function is this one. This is a good example. In the first function, we have a parabola. We have no domain restriction, all real numbers. In the second one, we again have a radical. So we take out what's under the radical, and we set it to greater than or equal to 0. We notice it's a quadratic, so we factor it. We find the roots. when x is 3, and when x is negative 3. And we place them on your number line. Because your quadratic is opening down, it looks like this as it intercepts your x-axis. And again, we want the positive. So our domain for this would be negative 3 to positive 3, regardless of what our final answer comes out as. In this one, we're going to do a composition of functions. We're going to put g of x into f of x.